Welcome back. So today's video is going to be a little bit different. What I want to do in this one is spend some time looking at various examples to see how we can start to identify which discrete distribution is appropriate for a given situation. So in this video, we'll go through a series of exercises, and for each example, we'll need to determine which distribution fits the scenario, what are the appropriate parameters, and then find a probability, expected value, and or variance. So the key thing I want you to watch for in this video is how we're deciding which distribution is appropriate. So let's look at the first of 5 examples. So we have an oil prospector who is planning on drilling a hole or a succession of holes in a given area to find a productive well. The probability that any random hole yields a productive well is 0.25. Here's what we want to know. We want to find the probability that the third hole drilled is the first to be productive. So we're looking at a situation where we want to know how many trials it's going to take until we're successful at a certain event. We have a constant probability of success, p equals 0.25. Our question here is how many trials or holes do we need to drill until we have a productive well or a success? That makes this situation a geometric distribution. So the geometric distribution probability then that y is equal to 3. The third hole is the success, the 2 previous are failures, so we get about a 14% chance. Take a look at another situation. If the prospector can only afford to drill 10 wells, what is the probability that he or she will fail to find a productive well? Here, a few things have changed. The probability of success is still constant, still 25%. However, we now have a fixed number of trials. We're going to drill the 10 holes. So then the probability that we don't find any successful wells in the 10 holes is a binomial probability. So to find the probability here that the number of holes that are successful, y is equal to 0, we get 10 choose 0 times 0.25 raised to the 0th power times 0.75 raised to the 10th power, 0.056. So there's about a 5.5% chance that we won't be successful, even if we're drilling 10 holes. Let's take a look at a new example. We have an early warning detection system for aircraft that consists of 4 identical radar units operating independently of one another. Each one of them has a probability of 95% of detecting an intruding aircraft. We would like to find the probability that an incoming aircraft goes undetected. Now we have a constant probability that each unit detects the aircraft, 95% probability. There are a fixed number of trials. We only have 4 radar stations. If an aircraft goes undetected, all 4 of those radar stations will need to miss it. So because of our constant probability and fixed number of trials, this is another example where we'll need to use the binomial distribution. Here, in order for the aircraft to go undetected, all 4 stations will have to miss it. So we're looking at the number of stations that detect the aircraft as being 0. Let's look at 2 more scenarios. We have 25 airline pilots who are eligible for promotion to captain. However, the airline is having a rough fiscal year and has decided to, out of the 25 who are eligible for promotion, randomly promote only 8 of them. Of the 15 male pilots who are available for a promotion, 3 are promoted. Of the 10 female pilots eligible, 5 are promoted. Is this evidence of gender discrimination against the male pilots? So in this case, we have a fixed population size. There are 25 airline pilots that we get to choose from with 2 groups, male and female. Our question really comes down to this: how many of a particular group are selected? What's the probability that we would observe a particular number? So this actually becomes a hypergeometric distribution. Out of those big N equal 25 pilots available for promotion, we're going to choose 8 at random. Out of the 10 female pilots, this instead of a little n should be a little r, how many of them, or what's the probability that we would choose 5? So even though this seems like an unlikely event, this would happen about 11% of the time, according to the hypergeometric distribution. So maybe there isn't a case for discrimination after all. So when do we use each of these distributions? We've covered 5 discrete distributions. Let's go through each one. So we'll use a binomial distribution when there are a fixed number of trials, each with constant probability of success. What we want to know, out of those n trials, how many were successful. With the geometric distribution, we're actually looking for the first success. So we're going to keep trying the experiment until we hit 1 success with constant probability. The negative binomial is just then an extension of the geometric. Here we're looking for the rth success, maybe the second, maybe the third, maybe the fourth, or so on, still with that constant probability. The hypergeometric, this is a little different from the other 3. The hypergeometric distribution should be used when we're sampling from a fixed population and looking for membership in some special characteristic. Now the last discrete distribution, the Poisson distribution, this is one that is a bit easier to tell apart from the others because it's a count variable. So we're looking at how often a specific event occurs. So those are the 5 discrete distributions that we have covered so far. In the next set of videos, we'll actually shift our attention over to continuous distributions. We'll see you then.